Good afternoon, everybody. Yeah, so I think starting January, I've been teaching in classes, so hopefully you guys will be like students and encourage me, and when I say good afternoon, you all shout, good afternoon, teacher, something like that. Anyway, hopefully you guys can do that with me and help me do this. I don't know whether you could say I'm a hacker. I'm probably not a hacker. I do develop a little bit. My main field is in computational neuroscience. I'm more of a researcher than anything else. So what I'm going to be presenting is stuff that I presented in Switzerland and Germany. It's my research, it's my thesis, it's about my thesis. And I'm going to, this is, as you can see there, it says it's a concept proposal presentation. This is what I'm hoping to be able to do in the next few years based on the research that I did for my doctorate. And so the title of this talk is Catch Me If You Can. And I'll be talking about improving the perception of contrast by introducing the convergence of retinal neurons. Okay, the second bit of the title is a bit much, but you'll probably understand what this is all about by the end of the talk. And you'll understand why it's called Catch Me If You Can. Hopefully, I'll ask the question at the end. Now, as he asked you, how many have watched the movie Catch Me If You Can? Excellent. How many have watched White Collar? Yeah, I think there are more people who've watched White Collar than Catch Me If You Can. Now, I will play a short video, and then this is, yeah, well.
Known as the world's greatest imposter, and no wonder. In the course of my nefarious career, I've found myself off as a doctor, lawyer, college instructor, stockbroker, and airline pilot. To become an airline pilot, I merely bought a plastic ID card for $5, affixed an airline logo from a model plane hobby kit, and in no time at all was co-pilot for a major airline. As a bogus lawyer, I actually worked on a state attorney general's staff. For 6 years, I also cashed over $2,500,000 in bad checks in 26 countries. Ultimately, I was sentenced to 72 years in prison. I served 1 year in France, 1 year in Sweden. I then served 4 years in a federal prison in this country. Paroled, I now devote my life to the prevention and detection of crime. Signed, Frank William Abagnale.
Did you ever give anybody medical advice?
Yes, I worked for a year as chief resident of a hospital.
Can I ask you, number two, which hospital?
It's the Cobb County General Hospital in Marietta, Georgia.
Did anybody get well into you, or was it vice versa?
Yeah, I had no problems.
You didn't feed the big jobs,
No.
just fingernails, right? Okay.
Number two, I imagine you mind embarrassing questions, so forgive me. This parole you have, is it real? My parole? Yes, sir. Yes, it expires in 1981. Will the real Frank William Abagnale please stand up? Frank, folks.
That was a really, really old production, but Frank William Abagnale was the most successful bank robber from the ages of 16 up until 19. So he did all these things when he was 16, as in he started all the flying. I think he went to 26 countries. He cashed checks in over 26 countries. While between the ages of 16 and 19. So I don't know. I just think that is like one of the most incredible things I've heard. But how many of you have heard of the story of the princess and the pea? Oh my God, okay. I don't know whether anybody can recount. In the story of the princess and the pea, a prince is looking for a princess, and the only way he could find the right princess is if he would stack mattresses and put a pea at the bottom, at the lowest mattress, beneath the lowest mattress, and the princess would be the one who could feel that there was a pea at the top. So that's the story of the princess and the pea. Now, you guys must be wondering, what's all this about? My main question to you is this. What do you think is the common factor between the movie Catch Me If You Can, the story of the princess and the pea, and vision? Wow, okay, there's already a response. There we go. Huh? Fraud. Okay. No, but hopefully at the end of this, I'll tell you what the common factor is between the three. How many of you know what the term visual acuity means? Who knows what visual acuity is? Okay, how many of you have been to the doctors to have your eyes checked? Okay. Especially if you wear glasses, for sure, you've had to go and had your vision checked. So what happens is, they usually have something known as a Snellen chart, okay? And you've been asked to read from the top to the bottom, or usually actually they should start from the bottom to the top. And you've had the phrase, do you have 20/20 vision? I hope. When someone says you have 20/20 vision, it is based on how well you see, or your visual acuity. Now, how well someone sees or is able to see is what is referred to as your visual acuity. When you're said to have 20/20 vision, it means that you're able to read everything from the point 20/20 here, from this point on all the way up. The poorer your eyesight is, so the next, if you can't read this line at line 8, but you can read line 7, then you're said to have 20/25 vision. So how they came up with this was that they put this chart 20 feet away from you. They put up the chart, and you're asked to read. That was a long time ago. I think they've improved this system, but it's similar to this. Whatever method they use to check your visual acuity, it still relates to this chart. And if at 20 feet you're able to read at the line 8, then you're said to have 20/20 vision. The first 20 indicates the feet from the distance from you to the Snellen chart, and the second 20 indicates the majority of, whether majority of the populace is also able to see that amount of, read that well, or see from that feet, and just see that line. I don't know whether I've explained that very well, but if you're said to have 20/200 vision, okay, let's just move up there. That means that you can't read any of the letters below that, but you can read the line, the first line. That is the E. So usually we use the Snellen chart to determine someone's visual acuity. And so when you hear me saying improving from, say, 22,000 to 2,200, you have sort of an idea of how poorly someone sees. Yeah. Okay. So visual acuity, I guess I could say, is based on 3 things. The first thing is the optical and neural factors, but the first thing is the focus within the eye, then the state and the function of the brain, and then the faculty of the brain. So I'll ask you, how do we see? How can you explain how someone sees? Who can briefly tell me how we see? Come on, how many did biology? Okay. Yeah.
So we get like 2 different images from each eye, and then our brain tries to to merge the two together and try to form an image. So, and most of the time what we see, it takes maybe seconds.
Yeah.
Based on a previous experience of that object. So our brain merges all that and then gives us the image.
Yeah, excellent. Okay, so it's very similar to what he said, but the most important thing you need to know is that there has to be processing within the brain so that you can be able to see. I mean, if there's nothing happening in the brain, then, or in the visual cortex, then you won't be able to see. So for you to see, there has to be some interpretation that happens within the brain. So the first and most important thing, when light goes through the pupil, it goes to the back of the eye, which is known as the retina. Now, the retina comprises of a myriad number of neurons, but the most significant number of neurons, there are 5. The first one is the photosensitive neurons, which are the rods and the cones. I hope you guys remember those things in biology. And then the next layer are the horizontal cells, then the next layer are the bipolar cells, and then the next layer we have the amacrine cells, and then the final bit we have the retinal ganglion cells. So why am I talking about all these things? So the nervous system consists of both the central nervous system and the peripheral nervous system. And the nervous system contains the neurons, about 100 billion neurons that are found within the brain and the spinal cord. And then the peripheral nervous system links the central nervous system to the skin, muscles, and the glands. Now, what is a neuron? A neuron comprises predominantly of 3 main parts. So we have the cell here, or the soma, if you want to be more whatever. And then we have the axon, the bit that goes like this. And then we have, at the end there, we have the axon terminals. At the beginning here, the cell consists of what is known as dendrites. Now, the dendrites get information from another cell. So one cell connects to another cell, connects to another cell, so that's how information moves from, say, the eye to the brain. And information moves along the entire system. That's how that happens. Now, in the retina, these connections, the neurons that are there, I mentioned them, we have the light-sensitive neurons, the photoreceptors, the horizontal cells, the bipolar cells, blah, blah, blah. But the most intriguing thing that happens with our eye is that when light moves from the pupil to the back of the eye, information is not processed like this. The light will go to the end, to the extreme back of the eye, and then moves back in this direction. It's an interesting phenomenon. I don't think there's anything that we've seen that's like that anywhere else. But it's fascinating, and nobody can tell you the reason for this. However, once the information comes back up this way, for the information to get to the brain, it goes through the optic nerves. Now, I'm sure you guys have heard of the optic nerves. What the optic nerve is actually, that's the axon of the retinal ganglion cells. So that's why I was showing you the image of the neurons, so that you can get to understand what the optic nerve actually is. Now, having said all this, maybe one thing I would like to tell you is that 50% of the cases we have for blindness are caused due to degeneration of some of the retinal neurons. So what option is there for someone and the sad thing about this is that once the retinal neurons degenerate, there's no way they can regenerate. If the neurons can't regenerate, that means that there's no way you can correct your vision. And so it is upon researchers, the onus is upon researchers to come up with ways to help 50% of the people who have blindness due to retinal degeneration. And that is what our research, or my research, has been all about. So now I'll get to explain to you what we're talking about. Let me go back and get the, 1 second. So when I talk about improving the perception of contrast by introducing the convergence of retinal neurons, the impact of our research is so that we'll be able to help inform the design and the development of retinal implants, so that for people who are blind due to retinal degeneration, they're able to see. Now, for you to be able to see, I'll give you an example. You walk into this room and everything is black. The chairs, the table, everything, the walls, everything. How will you be able to make out what is a chair and what is a table? Can anybody tell me? How would you be able to make out what is what? And say everybody's dressed in black and covered in like a black hoodie from onesie from the top to the bottom. How are you going to be able to distinguish what is what? You won't be able, oh, okay. Yeah, okay, that is a sense that you need to have, right? Another, so yes, maybe through touching. Oh, yeah, okay. Sorry? Oh, by the shapes, yes. But say everything is made out of the same material, and if everything is made out of the same material and having the same texture, then it will be very difficult even to make out that there's a different table. I mean, what you're seeing there is a chair as opposed to a table, because in the entire room. So what happens is, for you to see, there needs to be the perception of contrast. I don't know, I hope you've seen that link. There has to be contrast for you to see. And how well you perceive contrast allows you to see better. The better you can perceive contrast, the better you see. The better you see. And so for those who have degeneration or neurons that have degenerated, they can't perceive, most of the time they can't perceive contrast. And so it's our job to help them perceive contrast, hopefully by the work that we do. So my work was to come up with a computational simulation of the functionalities of the retina, so that we can be able to see, okay, how does the retina function? If the retina functions like this, can we be able to come up with a model that replicates that functionality? And the three main functionalities of the retina are adapting to light, contrast gain control, and spike generation. I probably won't go into detail about that in this forum. Yeah. Okay, what I'll tell you is that we had to look at existing models, simulations of the retina, and see how we could improve them. And what we found out was that most systems or most simulations were either rod-inspired or cone-inspired. So if you remember what I said at the beginning, the photoreceptors or the light-sensitive neurons are made up of two groups. We have rods and cones. And so most simulations were based on the cone system. And the reason for that is that the cones are the ones which are predominantly used for daylight vision. Let me put it as simply as that. And the rods are the ones which are used predominantly for night vision. However, based on recent research, it has been determined that this is sort of a fallacy. The truth is that cones are used to process lightness and rods are used to process darkness. Now, with this new information, we came up with the first model of the retina that incorporates or allows for the convergence between rods and cones. So the two systems have to work together so that they can improve vision. So imagine you walk into this room from outside and everything is dark, right? And it's still daylight. So it will be really difficult to process that information if only the rods are working, because maybe there's light here, there's shade here. So there are places where there's darkness, there are places where there's light. And so for you to be able to process the entire environment or system, then both the rods and cones have to be working well and working in conjunction with each other. So our model was the first system that simulated the convergence between the two systems, and we needed to determine what was the significance of converging the two systems. And what we came up with after a myriad of tests. So that is sort of, anyway, this is for like, I won't get into that, but if you have any questions afterwards, you can definitely ask me. So the first thing we did was to replicate a biological retina. And for our system, we had to verify that this, it actually replicates biology. And so we did tests to determine that. And so in this, it's just one image of a biological evaluation of our system to determine, was it replicating biology as well as it ought to have? And we got really positive results. But what is the significance of doing that convergence? And what we came up with, we came up with a quantitative approach which hasn't been used in our kind of research before. We used the signal-to-noise ratio. And then we compared our system with an existing an existing algorithm, an existing artificial algorithm, I don't know how else to put that, and contrast enhancement algorithm. And then we compared our system to removing the convergence and then added the convergence so that we could be able to scientifically determine whether our system was working appropriately. So I will sort of skip to the significance and the implications. So what we were able to determine was this, that when the signal-to-noise ratio is up, for the fast functionality of the retina and light adaptation, contrast is perceived in spite of varying luminance levels. So what that means is that you come into a room or you're given an image that is lighter by varying degrees. So I'll probably show you this image. So we introduced this image, the Lina image. And at the first point, we manipulated the lightness or the luminance of the image through 6 factors. I don't know how else to put that. But, and you can see it's getting brighter and brighter and brighter. What is the significance of adding the convergence? I'll just go directly and show you. Okay. Oops, I can't see. Okay, yeah. So I'll just give you the results, these results. So we were able to process the images to such an extent with the added convergence so that we're able to see the manipulated image even without, even when the light levels were so high that the natural image itself you couldn't see, implying that if you introduce that convergence, then you're able to allow for someone who has visual impairments to even see better. So, yeah, now this research has allowed for application in various fields, has been used in various fields, in obstacle avoidance in mobile robots, and in improving visual acuity, which is being done currently in Daniel Palenka's Hansen lab, which is in Stanford University, and has made a major breakthrough in the restoration of sight. And so they're able to improve vision for someone who has 22,000 visual acuity to about 2,200. Based on allowing for the convergence of rods and cones. So that's what they have done. But in the future, what are we hoping to be able to do? And in this near future, we hope to be able to develop a prototype that will explore the use of new technological findings so that to come up with a viable and hopefully cheap epi-retinal prosthesis. So what we want to do is come up with like a microchip or something like that that will be able to be implanted as a prosthesis or as a, I don't know, if when people don't have limbs, you give them the prosthetics, but now this is a prosthetic for the eye, a retinal prosthesis. Yeah, and then design and develop the circuitry needed to embed in a chip. So this is what we're currently working on. What I'm going to show you is with regards to what's happening in terms of technological findings. Do you get to see that in a minute? 1 second. I don't know how many have seen this video on Facebook. So in this video, they've invented a new kind of microchip that can be embedded into the spinal cord for people who are paraplegic so that they can be able to walk. And so in terms of new developments with regards to hardware or with regards to microchips, the technology has moved so much forward. Has moved in leaps and bounds. And instead of having the stuck or the static old kinds of microchips, now they're flexible and actually better adaptable to different kinds of, to be inserted within the body. So imagine something as flexible as this being inserted into the eye or into the back of the eye to be able to help with visual perception or improve someone's visual acuity. So for me, that is the future. I'm hoping to be able to come up with something that can be inserted in the back of the eye of people with poor vision or poor visual acuity so that they can be able to see better. Pretty much that's it. Now, I don't know how many of you would be able to now tell what the common factor is between the movie Catch Me If You Can and the story of the Princess and the Pea and Vision. What do you think the common factor is?
Contrast is the first thing that comes to mind.
Yeah.
What about contrast?
It's in the title, Catch Me If You Can.
Catch me if you contrast, catch me. It's staring me in the face, isn't it?
It is actually.
And everyone else in the room knows except for me. Catch me if you can. Contrast, catch me. I'll just say it random. Contrast, it applies to vision, but it also applies to feeling. I know humans are more, have a greater ability to recognize contrast in temperatures, contrast in vision, than we can in just seeing absolutes. We're better at dealing with, I don't know. I'm baffled.
Yeah, actually very close. So maybe somebody can close that link. Anybody? Clement? Come on. Or anybody else? I repeat, oh, okay, here we are. Oh, I repeat the explanation of the princess and the pea.
Yeah, just
okay, so a prince wanted to find a princess. And for him to determine who the right or who was the most princess of the princesses, he put a pea at the bottom of a stack of mattresses, and the one who could feel that there was a pea at the top is the one who was a princess. Mm-hmm. Wow, okay, I see I have back there. I'm sorry, this is extremely more scientific than anything. But in terms of development, I used MATLAB and probably 5 predominant algorithms. There's the Mike-Leese-Menton function, low-pass filters, the Gaussian, yeah, anyway. I used a couple of those to be able to come up with the simulations necessary for us to determine the significance of the convergence. So that's the programming aspect of this. Here we go.
I think the common factor is that something is trying to be caught, catch.
Yeah.
That's the common factor.
Yes. Okay. Good. Good. Anybody else? Comment? Did you want to go? Oh, okay. Ray, have you?
I'm going to ask you after you're done.
Clement, did you want to go? Yeah. Here we come. And then I'll probably explain a little.
I think maybe the contrast makes a difference.
Yeah.
So if you can, I think the contrast is like maybe like if you could get the contrast, you can make the difference. You can tell what something is.
Yeah.
So I think maybe it's like the P. Someone who can feel that P can make the difference between a good princess and a bad princess.
Excellent. So that's pretty much it. In the movie Catch Me If You Can, Carl Hanretti is trying to catch the bad guy, Frank Abagnale. In The Princess and the Pea, okay, let me tell you what the common factor is. For you to see, you have to be able to perceive contrast. That's as simple as it is. And so you kind of have to run after contrast to catch it. And so for those who don't have, whose retinal neurons have degenerated, then you have to help them catch the contrast or be able to perceive the contrast, like in Catch Me If You Can and in the story of The Princess and the Pea. You have to someone has to be sensitive to the existence of contrast to be able to see, pretty much. I hope that sort of ties in everything. Anyway, thank you.